Hi! Today we're going to learn about the comparison theorem in calculus. Let's say we have to prove that the integral from 1 to infinity of 1 over x cubed plus 3 is convergent. So how do we do this? Well, there are two ways. First, we could try and solve this integral to see whether it is convergent or divergent. And the second one is where we use, and the second way to figure out whether this is convergent is to use something called the comparison theorem. So the comparison theorem says that if f of x is greater than 0, greater than or equal to 0, or less than or equal to g of x on the domain of the integral that you're trying to compute, and if g of x is convergent, so convergent, I'm just going to say CON for short, if g of x is convergent, then that means that f of x is convergent too on that integral. So we know that, so let's say that f of x is smaller than or equal to, or less than or equal to g of x, and greater than or equal to 0 on the interval of the integral, so for all x on that interval, then if the integral of g of x from a to b, or a to infinity, of the integral of g of x is convergent, dx is convergent, then the integral from a to b of f of x dx is also convergent. So let's see an example of this. But before we do that, get this written down or remember it, because I'm going to have to erase it. So now let's look at an example. We have the function 1 over x cubed plus 3, and we should have dx here. So we have f of x is equal to 1 over x cubed plus 3. So we have to prove that this is convergent. So to prove that this is convergent, we need to have this be greater than 0 on the domain of the integral. So from 1 to infinity, we know that all x's will have to be greater than, or from the all x values from 1 to infinity, we know that all y values on this function will have to be greater than or equal to 0. So we know that f of 1 would be 1 over 1 plus 3, which is 1/4, and f of infinity would also be positive. We also know that any positive number that we plug into here would also be greater than 0, and we know that all the values between 1 and infinity are positive. So that means that all the values, x values, from 1 to infinity, when you plug it into f of x, the y values that come out are all positive. So we know that f of x is greater than 0, greater than or equal to 0. And now we need to find a function that it is less than or equal to, so g of x. So we have to find a function, g of x, that f of x, which is 1 over x cubed plus 3, is less than or equal to. So let's say a simple function that we know is convergent. So to prove convergency, we need to know that g of x is convergent. So to do that, we have to find a simple function that we know, which we know is convergent, that is greater than 1 over x cubed plus 3. So a simple one would be 1 over x cubed. We know that this is greater than 1 over x greater than or equal to, or greater on this domain is greater than 1 over x cubed plus 3 because the numerator is the same, but the denominator is smaller. So we have g of x is equal to 1 over x cubed plus 3. So we know that the integral from 1 to infinity of g of x, which is 1 over x cubed plus 3, is convergent. But just to make sure, let's actually do it. So we have the integral from 1 to infinity of 1 over x cubed dx would be equal to, so we know that this is also equal to x to the negative third power. So that means that this integral would be equal to negative 2 times x to the negative 2 power, or negative 2 over x squared. So negative 2 over x squared. And because this is a definite integral, we have to solve it from infinity, or 1 to infinity. So we get negative 2 over infinity squared minus negative 2 over 1 squared, which is negative 2. So we have plus 2, which gives us negative 2 over infinity squared is 0 plus 2. So we know that g of x is convergent on this integral because the answer comes out to 2, which is convergent. So because f of x is less than or equal to g of x at all x's from 1 to infinity, and it is also greater than 0 for all x's from 1 to infinity, and because g of x is convergent, we know that f of x would also be convergent. So therefore we get f of x is convergent, or it's not f of x, it's the integral of f of x. The integral from 1 to infinity of f of x dx is convergent. So now let's try to figure this out or look at this graphically. So take a moment to go over this and write it down, and then we'll move on to the next thing. So let's first erase this. So let's try and understand the comparison theorem graphically. So let's say we had a graph, or a Cartesian plane, this is the y-axis, or this is the x-axis, sorry. This is the y-axis. So let's say that we had a function that looked like this. And let's say that we were given this function as a number, or as in x's, so we had f of x is equal to some value, or some function, so we don't know what this actually looks like. And we need to use the comparison theorem to figure out whether this is convergent or divergent. And let's say that we want to find the integral from here to here, or from here to here. So we don't know whether, or actually, because we would know that that would have to be convergent, let's say that it goes like this forever. It reaches an asymptote at y equals 0. So let's say the function is like this, because we know that if we found it from here to another point, that would have to be convergent. So let's say, so we have this function. Now according to the comparison theorem, and we have this integral from, let's say, 2 to infinity. This is the integral from 2 to infinity. And let's call this function, then, this blue function, f of x. So we have the integral of f of x the integral from 2 to infinity of f of x dx. Now we know that this integral has to be greater than 0 on its entire domain of the integral. So as you can see, from here to infinity, so from 2 to infinity, f of x is greater than 0. So that satisfies the first condition of the comparison theorem. So we know that this integral is greater than or equal to 0. So now how do we figure out whether this is convergent? Well, let's say that we knew another function. Let's say that this function looked like this. Sorry, it has to be, whoops. Let's say that this function looked like this. And let's say that this black function here is g of x. And let's say that we knew that g of x from 2 to infinity, the integral of g of x from 2 to infinity was convergent. So the integral from 2 to infinity of g of x is convergent, so CON for short. So if we have a finite area under the curve from 2 to infinity of g of x, so if we have a finite area under the curve from 2 to infinity of g of x, so that would be, let's say, this area, and it keeps going. So if we knew that we had this finite area, then that means that any function that is greater than the lower bound here being in this function y equals 0, so that means that any function that is greater than this lower bound here, but less than this function on the entire domain of the integral, so on this entire part that we're finding the area of, also has a finite area. So because this function here is inside, let's say, this shape, so we have the shape that is created because of from these two, or this one bound at 2 and this other bound at infinity, and the curve and the line y equals 0. So we have the shape formed. And if we know that this shape has a finite area, so let's say that this shape was like this, so we'll take this analogy, so we have a shape like this, then we know that any other shape that has this side, so this side, and also this side, and is smaller than the shape that is originally created, or the shape of this function g of x that is created when you have g of x, so that is smaller than, let's say, this triangle here, you know that any shape that you create within here, be it like this or like that, or like that, any shape like that will have a finite area too. So that's how the comparison theorem works and why it is valid. Today we learned about the comparison theorem in calculus. Thank you for watching this video.